All right, we're getting ready to start the chapter on gases. And so in this video, we're going to look at an introduction to gases, and we're going to focus on one of the properties of gases, and that is gas pressure. So I'm going to start by talking about some general characteristics of gases. Unlike liquids and solids, where the molecules are relatively close together, in gases, they're relatively far apart. Another big difference is while solids tend to keep their shape and they tend to keep to a specific volume, when we go to the liquid phase, they no longer keep their shape, but they do keep their volume. Gases, on the other hand, are going to expand to fill whatever the size of the container they're placed in. And so gases can be expanded infinitely, and because the molecules are so far apart, they're relatively easy to compress, at least compared to solids and liquids. Now, the four fundamental properties of gases that we're going to focus this chapter on exploring are pressure, volume, temperature, and moles. And I have the units that we use for each one of those properties listed here. As we're doing calculations and things, we'll use particular variables to represent these. Some of these are obvious. For pressure, we use P, volume, we use V, temperature, we use temperature, or T rather, and for the moles, we're going to use N. And what we're going to do on the rest of the video is focus on gas pressure, because I think most of these other things we're relatively familiar with. Volume is just how much space it takes, the temperature, and then the moles are, how many molecules there are in the sample. So the best way to understand gas pressure is to think about what's happening on the microscopic or the molecular level. And so gases are composed of particles that are moving randomly and very fast in their containers. Now, they don't move in random directions. They move in a straight line until they collide with either the walls of the container or until they collide with one another, and then they bounce off. The pressure that a gas exerts is the force exerted by the gas molecules as they strike the surfaces around them. So as these molecules are bouncing into the surface, that's what creates the gas pressure. And the pressure of a gas depends on the concentration of molecules, right? So the more molecules there are per unit volume, the more often a molecule is going to be striking the surface, and so the pressure is going to go up. It also depends on the kinetic energy of the molecules. So if they have more kinetic energy, that means they're moving faster. So if they're moving faster, then when they hit the surfaces, they're going to be hitting them harder, and that's going to yield a higher pressure. But also, if they have a higher kinetic energy and they're moving faster, then they're just going to strike the walls more often. And so not only are the impacts more forceful, but there are more of them. And so the more molecules we have, the pressure goes up, and the faster the molecules are moving, or the higher kinetic energy they have, the higher the pressure is. So I wanted to talk about some of the aspects of atmospheric pressure that we experience every day. So as the Earth's atmospheric pressure varies, it creates a lot of the weather phenomenon that we experience. And so when you see weathermen and they have these maps where they have the H's and the L's, right? The H's indicate regions of high pressure, the L's indicate regions of low pressure. And high pressures are typically associated with clear weather, and low pressure is generally associated with unstable weather. So thunderstorms, tornadoes, things like that are more likely to occur when the pressure is low. Another way that we're influenced by atmospheric pressure is that as our altitude increases, as we get further from the surface of sea level, the atmospheric pressure decreases. So when you're at sea level, the atmospheric pressure is roughly 1 atmosphere, and we'll talk about the units of pressure in a little bit. As we go to higher altitudes, the pressure decreases. And so if you're living in Colorado, your average air pressure is going to be, atmospheric pressure is going to be lower than what we have here in Atlanta. Or if you're climbing Mount Everest, most climbers need to carry oxygen with them because the atmospheric pressure is so low that there's not enough oxygen to sustain life. So there are a lot of different units that we can use to represent the pressure. And you can use this table as sort of a conversion factor guide. If I want to convert between any one of these units, I can just set the two entries equal to each other. So if I wanted to know, for example, how a pound per square inch compares to a torr, I would just write that 14.7 psi is equal to 760 torr. And I could use that conversion factor to go back and forth between psi and torr. The ones that we'll use most commonly in this course are probably atmospheres, but then you'll also see problems where we deal with torr or millimeters of mercury. And it's important to notice that a torr is the same thing as a millimeter of mercury. It's kind of like milliliters and centimeters cubed. We can use those interchangeably. You may also see some problems where we deal with pascals, which is the SI unit of pressure, or kilopascals, which is, the kilo prefix works just like it has when we've used it in the past. What we're showing here is how a barometer works. And so this is a device that we can use to measure atmospheric pressure. And so we have two competing forces. So what we do is we take a tube that's evacuated of any gases. And so we have a vacuum inside the tube. And then we invert that and stick it into a pool of mercury. And so there are some different forces acting on the mercury, causing it to move up into the tube. So we have atmospheric pressure that's pushing down on the surface of the mercury. And so that's going to want to cause the mercury to move up into the evacuated tube. But we also have the force of gravity that's working against the mercury wanting to move up in the tube. And so the way we can measure atmospheric pressure, the higher the atmospheric pressure is, the harder it's going to be pushing down on the surface of the mercury, and the more it's going to want to make the mercury move up in the tube. And as long as we're not moving the barometer to vastly different distances from the center of the Earth, the force of gravity is the same. So the force of gravity is basically a constant. And so as the atmospheric pressure changes, if the atmospheric pressure increases, the mercury moves higher in the barometer. As the atmospheric pressure decreases, the mercury would move lower in the barometer. Now, mercury made a fairly good substance to use in terms of measuring pressure, but of course it's toxic. And so a lot of barometers that are made today probably don't use mercury. They probably use other substances. But traditionally, it was mercury that was used, and that's why we have these units in millimeters or inches of mercury. All right, so just two more slides. The first one, I just want to do an example of doing unit conversions with pressure. And so we have the table here where I just have the symbols and then how each of those units compares to 1 atmosphere, or how they compare to each other. And so we're given that the pressure on the top of Mount Everest is 228 millimeters of mercury, and I want to convert that to atmospheres and pascals. So let's do atmospheres first. So what we need to do is we need to find, 1 atmosphere, and then the other unit is millimeters of mercury. So we have 760 milliliters of mercury. So our conversion factor is 1 atmosphere is 760 millimeters of mercury. So then I can say I'm starting with 228 millimeters of mercury. Then in order for the milliliters of mercury to cancel out, I need to put that 760 on the bottom, the 1 atmosphere on top. And so when I do that math, I get 0.3 atmospheres. And so at sea level, the average atmospheric pressure is about 1 atmosphere. And at Mount Everest, you can see the pressure is about 1/3 of that. And that's a result of the lower concentration of air molecules, which is why many climbers need to carry oxygen with them because they can't get enough oxygen from the atmosphere to keep them alive. All right, now if we want to go now to pascals, I have it in atmospheres, and so I could go from atmospheres to pascals. So I could use that 1 atmosphere is 101 or 325 pascals, or I can go from the 228 millimeters of mercury, And I'm going to do it that way. So here I'm going to use that 760 milliliters of mercury is 101 325 pascals. So 760 milliliters of mercury, 101 325 pascals. And so I take 228, multiply it by 101,325, then divide that result by 760, and I get to three significant figures, 30,400 pascals. All right, and so just looking ahead, in the next section, we're going to use some online simulations to explore the relationships between the four fundamental properties of gases. We're going to look at how the pressure, the volume, the temperature, and the number of moles are related to one another.